There is a question that physicists have been sitting with since the early 1980s, a question that most of them do not discuss at dinner parties or mention in public talks, a question that lives in the footnotes of papers about quantum field theory and occasionally surfaces in the kind of late-night conversations that happen at physics conferences when the formal sessions are over and the beer is open and people start saying the things they think but do not usually say out loud. The question is this: is our universe real? Not in the philosophical sense, not the matrix question about whether experience is genuine, in a much more specific, much more technical, and in some ways much more terrifying sense. The question is whether the vacuum of space, the ground state of reality, the lowest rung of the energy ladder on which all of physics and chemistry and biology and everything else is built, is actually the lowest rung. Whether what we are sitting on is solid ground or whether it is, in the language of quantum field theory, a false vacuum, a local minimum that looks stable from the inside but is not, in fact, the lowest possible energy state of the universe. A ledge, not a floor. And whether at any moment in any location a quantum fluctuation could push a tiny region of space off that ledge and send it falling toward the true ground state, converting everything it touches, at the speed of light, into a different form of physics in which nothing we know can exist. The reason this question has left the footnotes and entered the main text of serious physics, the reason it is now something that the people who build particle accelerators and measure the properties of fundamental particles think about carefully and publish papers about, is a discovery that happened on July 4, 2012, in a tunnel buried 100 meters under the French-Swiss border. That was the day the Large Hadron Collider at CERN announced the discovery of the Higgs boson, and the specific mass of the Higgs boson, the number that came out of the data, 125.09 giga-electron-volts, give or take, sits in a part of parameter space that makes the vacuum stability question not academic but urgent. The universe, if the standard model is correct and no new physics modifies the picture, appears to exist in a state that is technically metastable, not certainly unstable, not certainly stable, metastable, probably fine for an extraordinarily long time, but not guaranteed, not safe in the way that a true ground state would be safe. The ledge, not the floor. To understand why this matters, why the mass of a particle discovered at a collider in Switzerland has implications for whether the universe is permanent, you have to understand something about what the vacuum of space actually is, because it is nothing like what the word vacuum suggests in everyday language. Most people think of the vacuum as nothing, empty space, the absence of matter and energy, the void between things. This is wrong in ways that are not merely technical but are profoundly important for how physics works. The quantum vacuum is not nothing. It is a seething, dynamic, extraordinarily complex medium that is the foundation on which all of reality sits. It has a structure, it has properties, it has an energy, the famous vacuum energy, the cosmological constant, the zero-point energy of all quantum fields. And it contains fields, quantum fields, stretched across all of space, that permeate every cubic centimeter of the universe, and whose values determine the masses and interactions of all the particles we know about. The most important of these fields, for the vacuum stability question, is the Higgs field. The Higgs field is not the Higgs boson. The Higgs boson is a ripple in the Higgs field, a quantum of excitation, a particle that appears when you hit the field hard enough with enough energy to shake a piece of it loose. The Higgs field itself is something more fundamental, a scalar field, a field that has a value at every point in space, and whose value in its ground state is what physicists call the vacuum expectation value. In the universe we live in, the Higgs field has a non-zero value everywhere in space. It is not zero in the vacuum, it is sitting at a specific value, roughly 246 giga-electron-volts in the units particle physicists use. And this non-zero value of the Higgs field in the vacuum is the thing that gives elementary particles their mass. Particles that interact with the Higgs field, quarks, electrons, the W and Z bosons, acquire mass through their interaction with this background value of the field. Particles that do not interact with it, photons, gluons, remain massless. The mass of every particle in the standard model is, in a precise technical sense, determined by how strongly it couples to the Higgs field and by the value of the Higgs field in the vacuum. This means that if the Higgs field's vacuum value changed, if it shifted to a different value, the masses of all elementary particles would change. The properties of atoms, which depend critically on the masses of the electrons and quarks that compose them, would change. The chemistry of molecules would change. The nuclear physics that holds atomic nuclei together would change. Everything would change. And if the Higgs field fell to a sufficiently different value, the true minimum of its energy, the changes would not be small adjustments, but catastrophic alterations that are incompatible with the existence of anything we recognize as matter. The question of whether our vacuum is stable comes down to the shape of the Higgs field's potential energy, a mathematical function that describes for every possible value of the Higgs field what the energy density of the vacuum would be. The potential energy is like a landscape, and the Higgs field is like a ball sitting somewhere on that landscape. If the landscape has a single minimum, one lowest point, and the ball is sitting in it, the vacuum is stable. It cannot go anywhere lower. It is on the floor. But if the landscape has two minima, one local minimum that is not the absolute lowest point, and a deeper true minimum somewhere else, then the ball could in principle tunnel quantum mechanically through the barrier between them and fall to the deeper minimum. This is the false vacuum scenario. The ball appears to be resting stably in the local minimum, but it is not in the true ground state. Given enough time, and quantum tunneling is probabilistic and can in principle happen at any moment, the field could jump to the lower minimum, converting a region of space to the true vacuum. The shape of the Higgs potential is not directly measured. It is calculated from the known properties of the particles that couple to the Higgs field, using the mathematics of quantum field theory. The calculation is extremely difficult. It requires tracking the contributions of all the particles in the Standard Model through many orders of perturbation theory, keeping track of quantum corrections at 2, 3, and 4 loops of precision. But it has been done, and done carefully, and the result depends critically on the mass of two particles, the Higgs boson itself, and the top quark, the heaviest of the 6 quarks, and the particle whose quantum corrections to the Higgs potential are by far the largest, because its coupling to the Higgs field is proportional to its mass, and the top quark is extraordinarily massive compared to all other fermions. Before the Higgs boson was discovered, its mass was unknown, and without knowing the Higgs mass, you could not calculate the shape of the potential. The top quark mass was measured at the Fermilab Tevatron Collider in the 1990s, and its value, around 173 gigaelectronvolts, was known with reasonable precision. But the Higgs mass was the missing piece, and when the Large Hadron Collider measured it in 2012 at 125 gigaelectronvolts, physicists immediately plugged it into the calculation. What came out was not reassuring. The combination of the measured Higgs mass and the measured top quark mass places our universe in a region of parameter space that is described in the technical literature as metastable. Physicists drew a phase diagram, a map of Higgs mass versus top quark mass, divided into 3 regions: absolutely stable, metastable, and unstable. The stable region is where the vacuum is definitively safe. The unstable region is where the vacuum is definitively unstable, and the universe would have already decayed. The metastable region is where the vacuum appears stable locally but is not the true ground state, where a quantum tunneling event could in principle trigger a decay to the true vacuum at any time. When the measured values of the Higgs and top quark masses were placed on this diagram, they landed in the metastable region, right on the boundary within the measurement uncertainties between metastable and stable, but nominally in metastable, probably metastable. Possibly stable if the measurements are slightly off, certainly not in the unstable region, but not in the safe zone either. This result, published in a series of papers in 2012 and 2013 by groups including one led by physicists Giuseppe Di Grassi and Gian Giudice at CERN, was covered briefly in the science press, with varying degrees of alarm, and quickly receded from public attention. But in the physics community, it has remained a quietly central concern, a fact about the universe that changes the character of the vacuum stability question from a theoretical curiosity to an observational result. We did not calculate a hypothetical scenario. We measured the Higgs mass. We measured the top quark mass. We plugged the numbers in, and the numbers say metastable. The calculated lifetime of the metastable vacuum, the average time before a spontaneous decay would occur, is extraordinarily long. The calculations give a number that is roughly 10 to the power of several hundred years. This is a number so large it bears no relationship to any timescale in human experience, or in the history of the universe, or in the projected future of stars and galaxies. The current age of the universe is about 13.8 billion years, roughly 10 to the 10th years. The calculated vacuum lifetime is 10 to the power of hundreds of times larger than that. In practical terms, the probability of a vacuum decay in the next trillion years is incomprehensibly small. On the scale of human life or human civilization or geological time, or even the time for the sun to exhaust its fuel, the vacuum is for all practical purposes completely stable. But this is where the nature of the problem asserts itself in a way that resists the comfort of those numbers. The probability of a vacuum decay in any given region of space in any given period of time is related to the volume of space being considered. The observable universe is an extraordinarily large place, and the universe extends almost certainly far beyond what we can observe. If the universe is infinite or even just very large, then the total probability of a vacuum decay happening somewhere at some time is not suppressed by the per-volume probability in the way that makes the number reassuring. An event that is extraordinarily unlikely per unit volume per unit time becomes effectively certain given enough volume and enough time. The universe has both. The calculation of a vacuum lifetime assumes a finite observation volume, and when you apply it to the actual scale of the universe, let alone an infinite or near-infinite cosmos, the comfort of the large number dissolves somewhat. But this is not quite the right way to think about the danger of vacuum decay either, because the danger is not primarily that it will happen in the future. The danger is that it may have already happened, somewhere very far away, and we would not know. This is the most philosophically jarring aspect of the vacuum decay scenario, and it is worth dwelling on at length because it is so different from every other existential risk that physics or biology or civilization has ever contemplated. Every other catastrophe that could threaten life on Earth, an asteroid impact, a nearby supernova, a gamma-ray burst, a supervolcanic eruption, comes with at least the theoretical possibility of warning. Light or particles or some signal precedes the event, or precedes the damage, or at minimum the event itself leaves time for some region of the Earth or the solar system or the galaxy to survive. Not vacuum decay. A bubble of true vacuum, once nucleated, expands at exactly the speed of light in all directions. The interior of the bubble has different physics. The Higgs field has a different value. Particles have different masses or no mass at all. Atoms cannot exist in any recognizable form. Chemistry is impossible. The bubble wall is a boundary between our universe and something completely alien, and because the wall travels at the speed of light, no information about it can precede it. Light itself is limited to the speed of light. The bubble wall is at the speed of light. There is no possible signal that could reach us before the wall does. There is no telescope sensitive enough, no detector subtle enough, no early warning system conceivable that could give us a single nanosecond of advance notice. The first indication that a vacuum decay event had occurred would be the event itself, existence, and then nothing, no in-between, and it would be not just Earth, not just the solar system, not just the galaxy. The bubble, once started, expands forever in all directions at the speed of light, growing larger with every passing moment, converting everything it encounters to the new physics. There is no force in the known universe that could stop it. The strong nuclear force cannot stop it. The bubble wall rewrites the laws governing the strong force as it passes. Gravity cannot stop it. The bubble wall rewrites the geometry of spacetime as it passes. There is no material, no structure, no technology conceivable within our physics that could resist or deflect or outrun a bubble expanding at the speed of light. Everything that has ever existed and everything that could ever exist in the reach of that bubble is converted permanently to something unrecognizable. Not destroyed in the sense of matter being turned to energy. Converted. The laws of physics inside the bubble are different, and the forms of organization that our physics permits, atoms, molecules, stars, galaxies, life, cannot be assembled from whatever the physics of the true vacuum looks like. What does the physics inside the bubble look like? This is a question that physics can partially answer, and partially cannot. The true vacuum of the Higgs field, the deeper minimum of the potential assuming it exists, would have a Higgs field value different from the current 246 gigaelectron volts. If that value were zero, all elementary particles that get their mass from the Higgs would become massless. Electrons would become massless, like photons. Quarks would become massless. The binding mechanisms that hold protons and neutrons together, which depend on the masses of quarks and the structure of the QCD vacuum, would be completely altered. Atoms, which exist because of the specific relationship between the mass of the electron and the energy scales of atomic physics, could not form. Protons and neutrons in their current form might not be stable. The entire chemistry on which biology depends, on which any complex material structure depends, would be impossible, not difficult, not unlikely, impossible, by the laws of physics as they would exist inside the bubble. Some theorists have explored what the true vacuum physics might look like in more detail, depending on the specific parameters of the transition. Some scenarios allow some form of bound states inside the bubble, new physics, completely alien, but not entirely featureless. Others result in what is essentially structureless plasma, a soup of particles that cannot organize into anything. The details depend on the specific form of the Higgs potential and on what other physics might exist beyond the standard model. But in no scenario that has been worked out does anything resembling life, or chemistry, or the material structures we know survive the transition. The bubble wall is the end of the world, not just our world, but the laws that make worlds possible. There is a specific type of event in the universe that is capable, in principle, of triggering vacuum decay rather than waiting for it to happen spontaneously. High-energy particle collisions. Whenever two particles collide at very high energy, they create a tiny region of extremely high energy density in a small volume of space. In principle, if the collision energy were high enough and the collision product were in the right quantum state, it could seed a vacuum decay event, act as the initial nucleation point for a bubble of true vacuum. This concern was raised, in various forms, in discussions about both the relativistic heavy ion collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN, and it contributed to public anxieties about these machines that physics had to address directly. The answer that physics gave, and it is a good answer, is based on cosmic rays. The universe has been bombarding Earth and every other object in the cosmos with high-energy particles since the beginning of time. Cosmic rays, protons and heavier nuclei accelerated by supernovae, pulsars, active galactic nuclei, and other astrophysical sources, arrive at Earth with energies that span an extraordinary range, and the highest energy cosmic rays have energies far exceeding anything the LHC has produced or will produce in any foreseeable upgrade. The highest energy cosmic ray ever detected, the Oh My God particle, recorded in 1991 by the Fly's Eye detector in Utah, had an energy equivalent of about 320 eV, which is roughly 40 million times the energy of the highest energy collisions at the LHC. If high-energy collisions could trigger vacuum decay, cosmic rays would have done it long before any human accelerator existed. The fact that the universe has been conducting particle physics experiments at energies vastly exceeding anything we can produce for billions of years without apparent consequence provides extremely strong evidence that laboratory particle accelerators cannot trigger vacuum decay. The LHC is safe. This argument is solid, but cosmic rays, as powerful as they are not infinitely energetic. There are theoretical limits to how high cosmic ray energies can go, the GZK limit, a cutoff above which protons rapidly lose energy through interactions with the CMB, and the energies at which vacuum decay might be preferentially triggered by collisions, are not well determined by theory. The cosmic ray argument provides reassurance for the energy scales of existing and near-future accelerators. It provides somewhat less complete reassurance for processes that might occur in the cores of neutron star mergers, or near the event horizons of black holes, or in the extraordinary energy densities of the very early universe. These are environments where the energies far exceed anything cosmic rays can produce, and where the question of whether vacuum decay has been triggered is in principle a concern. Of course, the fact that the universe still exists after 13.8 billion years, that it has survived billions of neutron star mergers and the formation of countless black holes, is itself evidence that these events do not trigger vacuum decay. But the logic is the same as the cosmic ray argument. Absence of evidence of catastrophe is not the same as proof of safety. The man most associated with the popularization of the vacuum decay concern, though he did not invent the concept, is Sidney Coleman, a theoretical physicist at Harvard who was one of the most gifted and beloved physicists of the 20th century. Coleman's two papers on the subject, published in 1977 and 1980 with collaborator Frank DeLucia, are among the most important papers in quantum field theory, and are still cited constantly today. Coleman had a reputation not just for his science, but for his wit, his teaching, and his ability to explain difficult concepts with unusual clarity and humor. His lectures at Harvard on quantum field theory were legendary. Physicists who attended them decades ago still describe them as the best scientific lectures they ever witnessed. And Coleman had a characteristic way of dealing with the existential implications of vacuum decay. directly, dryly, and with a kind of dark humor that acknowledged the absurdity of sitting in a seminar room discussing the possible non-existence of the future. In his 1980 paper with DeLucia, after working through the detailed calculation of how a vacuum decay bubble would evolve and what it would mean for the physics inside the bubble, Coleman and DeLucia added a brief remark that has become one of the most quoted sentences in the theoretical physics literature. They wrote, discussing the implications of their results, "The possibility that we are living in a false vacuum has never been a cheering one to contemplate." This is a sentence that rewards slow reading. It is funny, the elaborate academic understatement of calling the potential non-existence of everything not a cheering one to contemplate. It is honest. It acknowledges directly that the authors understand the emotional weight of what they are calculating. And it is, in context, a brief human moment in a dense technical paper about the mathematics of quantum tunneling, acknowledging that the people doing the calculation are people, and that the thing they are calculating matters to them in a way that goes beyond the technical interest. Coleman died in 2007, 5 years before the Higgs boson was discovered and the vacuum stability calculation became a question with real measured inputs, rather than a theoretical exercise with free parameters. He never knew where the Higgs mass would land. He never knew whether the numbers would come out stable or metastable. He calculated the consequences of both possibilities with equal rigor and equal care, and he wrote about both with the same combination of technical precision and dry, gentle wit. The field he helped create, the study of vacuum decay and false vacuums in quantum field theory, has outlasted him, and the discovery of the Higgs mass gave it a specificity and an urgency that his papers alone could not. There is a specific person who experienced the moment of the Higgs discovery in a way that most people who were not there have not fully appreciated, not for the personal triumph of the discovery but for what the number meant. When the ATLAS and CMS experiments at CERN announced the Higgs boson on July 4, 2012, with a mass of 125.09 gigaelectron-volts, the physicists in the auditorium at CERN cheered and wept and gave a standing ovation to Peter Higgs, who had predicted the existence of the field that bears his name in 1964, and was sitting in the front row, visibly moved, having waited 48 years to see his prediction confirmed. It was an extraordinary moment. One of the great scenes in the history of science, the old man who had been right for half a century finally seeing the vindication he had been owed since before most of his vindications were born. The cameras found Higgs. He was wiping his eyes. He said afterward that he had not expected to live to see it. What did not make the cameras? And what was happening simultaneously in the same room and in offices around the world as the data was presented was that theoretical physicists were reaching for their phones and laptops in the back of their programs and pulling up the phase diagram, the map of Higgs mass versus top quark mass divided into stable, metastable, and unstable, and placing the new measured value on it, finding where it landed. 125 giga-electron-volts. Top quark mass around 173 giga-electron-volts. The point on the diagram, in the metastable region, close to the boundary with stable, within the measurement uncertainties that would not be reduced for years. But in the metastable region, the celebration and the calculation happened simultaneously, in the same room, among some of the same people. The greatest discovery in particle physics in a generation contained, built into the specific number that was its central result, the implication that the vacuum of the universe might not be permanent. This coexistence of triumph and unease is one of the most characteristic features of theoretical physics at its frontiers. The discovery confirmed a prediction. It completed the standard model, filling the last gap in the most successful and precisely tested theory in the history of science. It vindicated decades of work by thousands of people and billions of dollars of investment in the most expensive scientific instrument ever built. And it told us that the ground we are standing on might not be the lowest ground available. Both things are true simultaneously. Both things followed from the same number. The universe does not organize its revelations for our emotional convenience. The standard model, whose completion was celebrated that day, is itself a remarkable thing, and the vacuum stability question cannot be fully understood without appreciating just how extraordinary the model is and just how much rests on it. The standard model of particle physics is a quantum field theory describing 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, and all of the known elementary particles. It was developed in the 1960s and 1970s by a remarkable collection of physicists: Glashow, Weinberg, Salam, Higgs, Englert, Brute, Nambu, Wilczek, Politzer, Gross, and many others, and it has made predictions that have been confirmed to extraordinary precision by experiments around the world. The anomalous magnetic moment of the electron, a quantity predicted by quantum electrodynamics, the electromagnetic sector of the Standard Model, has been measured and calculated to 12 significant figures, and theory and experiment agree to 12 significant figures. This is the most precise agreement between theory and experiment in the history of science. The Standard Model works. At the energies and scales we have probed, it works almost perfectly, but the Standard Model is not complete. Physicists have known for decades that it must be extended, because it does not include gravity. It has no quantum description of the gravitational force. It does not explain dark matter. Whatever dark matter is, it is not in the Standard Model's particle catalog. It does not explain the matter-antimatter asymmetry of the universe, why the universe contains matter rather than equal amounts of matter and antimatter. It does not explain the specific values of its own parameters, the masses of the quarks and leptons, the strengths of the forces, which must be put in by hand as measured inputs rather than derived from any deeper principle. The Standard Model is extraordinarily successful and clearly incomplete, and the search for what lies beyond it has been one of the defining projects of particle physics for the past several decades. The vacuum stability result is intimately connected to this search for new physics, because the metastability of the vacuum in the Standard Model is an extremely peculiar and suggestive fact. The Higgs mass and top quark mass, as measured, sit remarkably close to the boundary between stable and metastable, not just in the ballpark but within the measurement uncertainties, tantalizingly close to the boundary. This proximity has struck many physicists as unlikely to be a coincidence. If the fundamental parameters of the Standard Model were distributed randomly, the probability of ending up so close to the stability boundary would be very small. The fact that we are apparently close to it suggests that there might be some deeper principle, some symmetry or constraint that we have not yet discovered, that requires the parameters to be near the boundary or exactly on it. Some theorists have speculated that the true vacuum of the Standard Model might be exactly at the stability boundary, that the Higgs potential is designed by some mechanism we do not understand to be exactly at the edge of stability. This idea, called the multiple point principle or near criticality, is not an established theory but a hint, a structural feature of the Standard Model that might be pointing at something deeper. Supersymmetry, the theoretical framework that extends the Standard Model by adding a supersymmetric partner for every known particle, changes the vacuum stability calculation significantly. Supersymmetric theories have additional contributions to the Higgs potential from the superpartner particles, and these contributions tend to stabilize the vacuum, to push the parameters into the stable region. This is one of the reasons supersymmetry was attractive to many theorists even beyond its other virtues. But supersymmetric partner particles have not been found at the LHC, despite years of searching at energies where many models predicted they would appear. The simplest supersymmetric models are increasingly excluded by the data. More complex models survive but require superpartners at higher masses, which changes their implications for vacuum stability. The relationship between supersymmetry and vacuum stability remains an active area of theoretical work. There is another class of beyond Standard Model physics that would profoundly affect the vacuum stability calculation: right-handed neutrinos. Neutrinos, the lightest of the known fermions, almost but not quite massless, have masses that are not explained by the Standard Model in its minimal form. The discovery that neutrinos have mass was itself a sign that the Standard Model is incomplete. The most popular theoretical mechanism for generating neutrino masses, the seesaw mechanism, requires the existence of heavy right-handed neutrinos that have not been directly observed. If right-handed neutrinos exist at certain masses, their contributions to the Higgs potential can shift the stability boundary significantly, potentially moving our vacuum from metastable to stable, or pushing it further into the metastable region, depending on their specific properties. The vacuum stability question, in this sense, cannot be fully answered until we know what lies beyond the Standard Model, and we do not yet know that. The measurement of the top quark mass is another critical uncertainty in the vacuum stability calculation. The top quark mass enters the calculation through its quantum corrections to the Higgs potential, corrections that are proportional to the fourth power of the top quark mass, which means that small uncertainties in the mass translate into larger uncertainties in the stability result. The top quark mass has been measured at both the Tevatron and the LHC, and the precision of those measurements has improved over the years. But there is a subtle technical issue that has been discussed in the literature. The mass that collider experiments directly measure, the so-called Monte Carlo mass, extracted by comparing data to simulation, is not precisely the same as the theoretically well-defined pole mass, or the ms bar mass that enters the vacuum stability calculation. The relationship between these different mass definitions involves its own quantum corrections, and the conversion between them introduces uncertainties that are difficult to eliminate. Some analyses have suggested that these uncertainties are large enough to shift the stability conclusion from metastable to stable or vice versa. Getting the top quark mass right, in the theoretically unambiguous sense, is one of the most important measurements for resolving the vacuum stability question, and it is a focus of ongoing work at the LHC and at proposed future colliders. The proposed future collider that would most directly address this, the Future Circular Collider, or FCC, a 100-kilometer circumference machine proposed at CERN as a successor to the LHC, would measure both the Higgs mass and the top quark mass with dramatically improved precision, reducing the uncertainties enough to definitively determine whether the standard model vacuum is stable or metastable, assuming no new physics is discovered that changes the picture. The FCC would also be capable of probing for new physics at energy scales far beyond the LHC, potentially finding the supersymmetric particles or other new phenomena that would modify the stability calculation. The vacuum stability question is one of the explicit scientific motivations for the FCC, which gives you a sense of how seriously the physics community takes it. Peter Higgs, who gave his name to the field and the boson and who wept in the auditorium at CERN when the discovery was announced, lived until 2024. He died at 94, 4 years before this script was written, having seen the particle that bore his name discovered, and having seen the implications of its measured mass worked out in detail. He was not a person who spent much time on the existential implications of his work. By temperament, he was a quiet, private, modest man who was somewhat uncomfortable with the celebrity that came with the Nobel Prize he received in 2013, and who did his best physics alone in a way that was already becoming unusual in an era of large collaborations. But the field he helped create, the physics of spontaneous symmetry breaking and the vacuum structure of quantum field theories, is the field in which vacuum decay lives. His 1964 paper, and the other papers by Englert, Brout, and others that accompanied it, are the foundation on which the vacuum stability calculation is built. Every time a physicist plugs numbers into the Higgs potential and asks whether our vacuum is stable, they are using the mathematical structure that Higgs and his contemporaries wrote down 60 years ago. The question of whether the ground we stand on is permanent is, in a very direct way, his question, even if he did not frame it in those terms. The emotional experience of being a physicist who thinks about vacuum decay is something that rarely makes it into the scientific literature, because scientific literature is not the place for emotional experience. But it is real, and it shapes how physicists engage with the subject in ways that are worth acknowledging. There is a specific cognitive move that you have to make, a kind of compartmentalization, to work productively on a calculation that has, built into its premises, the possibility that everything you have ever known and will ever know could cease to exist without warning. The calculation demands precision and care, and the suppression of distraction, and the fact that the thing you are calculating is your own potential non-existence is precisely the kind of distraction you have to suppress. Physicists do this. They are good at it. The compartmentalization becomes a professional skill, as natural as reading a paper or checking a derivation, but it breaks through sometimes. In conference talks, in late-night conversations, in the moment when you step back from the calculation and look at the phase diagram with the data points sitting in the metastable region and you allow yourself, for a moment, to think about what that means not as a technical result, but as a fact about the universe you live in. That moment is different for different people. Some find it exhilarating. The universe is stranger and more interesting than it would be if everything were safe and permanent. Some find it deeply unsettling in a way that does not fully resolve even after years of working with the concept. Some find it almost liberating. If the universe could end at any moment without warning, then the specific anxieties that fill ordinary human life are revealed as the small things they always were, and the fact of existence itself becomes more vivid. These are not scientific responses. They are human responses, and the fact that a calculation in quantum field theory provokes them is itself remarkable. There are philosophers and theologians who have written about vacuum decay, though not always under that name. The idea of a contingent universe, one whose existence is not necessary, one that could have been otherwise or could cease to be, is a very old one, and it has been the subject of religious and philosophical reflection for as long as people have thought carefully about the nature of existence. What vacuum decay adds to this ancient discussion is specificity and mechanism. The contingency of the universe is not just a philosophical intuition or a theological claim, it is a calculation. With specific inputs and specific outputs and specific uncertainties, the contingency is not vague but mathematical. The universe might be impermanent not because of some abstract metaphysical claim, but because the Higgs field might be sitting in a metastable state, whose decay rate can be estimated with computable error bars. This is a new kind of conversation between physics and the deepest questions of human thought, and it is one of the things that makes vacuum decay one of the most philosophically significant results in modern physics, even though most people have never heard of it. It is also, in a sense that is worth naming clearly, one of the strangest features of the human situation in the universe. We are a species that has existed for a few 100,000 years on a small rocky planet orbiting an ordinary star. We have been doing science in the modern sense for a few hundred years. We have been doing particle physics for about a century. And in the course of that century, we have discovered, through the careful application of mathematics and experiment, that the vacuum of space might be unstable, that the ground state of reality might not be the true ground state, that there might be a deeper minimum of the energy landscape of the universe, and that a quantum fluctuation in any region of space could, at any time, initiate a transition to that deeper minimum. We have calculated the implications. We have measured the parameters. We know where the answer sits on the phase diagram. And we know, with the same physics that tells us all of this, that if the transition has already happened somewhere in the observable universe, we have no way of knowing and no way of protecting ourselves. This is not a cause for panic. The timescale for spontaneous vacuum decay on the best current calculations is so long as to be completely irrelevant to any human concern or any civilizational planning. It dwarfs the projected lifespan of the Sun, of the galaxy, of stellar populations across the universe. On any timescale that matters to any being or institution or project that has ever existed on Earth, the vacuum is stable. The only emotionally appropriate response to the vacuum decay possibility is not fear, but something more like awe. Awe at the strangeness of the universe, at the depth of the questions that physics has learned to ask, at the specificity with which it can ask them, and at the remarkable fact that a species of primate that has been walking upright for a few million years has managed to work out, from first principles and carefully controlled experiments, that the fabric of reality might be impermanent, and there is still the possibility that it is not. The measurement uncertainties in the Higgs and top quark masses leave open the possibility, a real, non-negligible possibility, that the true parameter values land in the stable region of the phase diagram. New physics beyond the standard model, if it exists at the energy scales the LHC is probing or just above them, almost certainly modifies the stability calculation in ways that could move the result to safety. Supersymmetry, if it exists, stabilizes. Additional scalar fields, if they exist, can stabilize. Extra dimensions of space, if they exist, change the picture entirely. The standard model calculation that gives metastability is a calculation in the absence of new physics, and we know the standard model is incomplete. Whatever extends it may solve the vacuum stability problem, along with the other problems the standard model cannot address. We do not know yet. The answer requires better measurements and possibly new discoveries at higher energies than the current LHC can reach. The proposed FCC, if funded and built, it would take decades, could settle the question definitively, or at least reduce the uncertainties to the point where the answer becomes unambiguous within the standard model framework. In the meantime, the question sits open: metastable or stable? Permanent or contingent? Floor or ledge? The universe, as usual, is not telling us until it is ready. What it has told us, through the mass of a particle measured at a machine buried under the French-Swiss border on the 4th of July 2012, is that the question is real, that the vacuum of space has a structure that can in principle be unstable, that the laws of physics permit the existence of false vacuums, and that the parameters of our universe sit close enough to the instability boundary that the question of which side of the line we are on cannot be answered without better measurements than we currently have. That is not nothing. It is in fact an extraordinary thing to know. The universe has handed us a mystery about its own permanence and encoded the answer in the mass of a particle that was predicted in 1964 by a quiet Scottish physicist who hated the publicity and wanted only to understand why things have mass. We are working on it. We are building better detectors, running more collisions, refining the theoretical calculations, arguing in papers and at conferences about the right way to define the top quark mass and how to handle the higher-order corrections. We are, as a species, genuinely trying to determine whether the ground we stand on is the true ground or a ledge above a deeper minimum, and we are doing it with the tools of mathematics and experiment and the kind of patient, careful reasoning that has produced every major advance in the history of physics. Whatever the answer turns out to be, the asking of the question is one of the most remarkable things our species has done. To stand on the surface of a small planet, in the middle of a vast and mostly empty universe, and to work out from the motions of fundamental particles in an underground tunnel that the vacuum of space might be impermanent. To do that, and to keep doing the work to find out whether it is true, is an astonishing thing. Small and temporary as we are, we looked at the universe and we asked it one of the deepest questions it can be asked, and it almost answered. The number it gave us sits right on the boundary. It is telling us something. We just have not quite figured out what: the ledge or the floor, the metastable or the stable, the contingent or the permanent. The universe knows which it is. We are still working it out, one collision at a time, one calculation at a time, sitting in offices and running on computers and arguing in papers with the quiet, stubborn insistence that the answer is there if we look carefully enough. It probably is. It almost certainly is. And when we find it, it will be one of the most important things we have ever learned about where we are, or the question will answer itself, without warning, somewhere in the universe, while we are in the middle of looking, and there will be no one left to write down what it said.